This lecture is part of an online course on rings and modules and will be about duality of modules. So what I'll start by doing is just recalling duality of vector spaces. So suppose V is a vector space over a field K. Then we have a dual vector space, which is just the space of linear maps, homomorphisms from V to the field K. This is homomorphisms over K. And this is also a vector space. And we also have a natural map from V to its double dual. So you remember elements of the double dual are maps from V star to K. And if we've got an element V in V and an element F in V star, so F goes from V to K, then we can map F to K by mapping F to F of V, and this is linear in F, so this map from F to F of V gives you a linear map from the dual of V to K. So there's always a natural map like this. And now we can ask, is V isomorphic to its dual or the double dual? And if V is finite dimensional, the answer is yes. Basic result on linear algebra that if you choose a basis for V, this identifies V with an n-dimensional vector space, and the dual is also an n-dimensional vector space, so they're isomorphic. So V is isomorphic to its dual, but this is not really natural. In order to define an isomorphism, we have to pick a basis of V, and if we pick a different basis, we get a different isomorphism. However, the isomorphism V to its double dual is natural, because we've defined this map from V to its double dual, and if V is finite dimensional, this is actually an isomorphism. So in some sense, the isomorphism between V and its double dual is much better than the isomorphism between V and its dual. And you can ask what happens if the dimension of V is infinite. In this case, V is usually not isomorphic to either its dual or its double dual. For instance, suppose the dimension of V is just countable, so V has a basis V1, V2, V3 and so on. So the elements of V are things of the form sum of AI, VI, where almost all AI are 0. Well, elements of the dual of V consist of sequences BI where an infinite number can be 0, and this maps an element V of V to sum of AI BI. However, the space of all sequences where the BI's don't necessarily have to be all 0 can be is of uncountable dimension. So the dual of V is very much bigger than V, at least in general. What we quite often do is you can put a topology on V. For instance, suppose V is a vector space over, say, the reals or the complex numbers. What we can do is we can put a topology on V. For example, we can define spaces LP of n to be the sequences AI, with AI in, say, the complex numbers, such that the sum of AI to the P is finite. So this is a standard vector space in analysis, and this has a norm given by the pth root of this. Here we take n, we can either take n to be the positive integers 1, 2, 3 and so on, or more generally we can take n to be a measure space, and then we integrate a function over this measure, the pth power of a function over this measure space and so on. Anyway, I'm just going to keep this to be the positive integers for simplicity. Then it has a dual consisting of LQ of n, provided 1 is less than P is less than infinity, where 1 over P plus 1 over Q is equal to 1. For example, if P and Q are both 2, then this is essentially a Hilbert space, and this just says the dual of a Hilbert space is a Hilbert space. So you, furthermore, you find the dual of LQ of n is then just LP of n. So LP of n is actually isomorphic to the double dual of LP of n. So sometimes spaces are isomorphic to their double duals, provided you put the right topology on them. However, even if you put a nice topology on them, this can still fail. For example, if you take V to be C naught of n, which is sequences A1, A2, and so on tending to 0, or if more generally, if n is some sort of locally compact space with a measure, it might be functions that vanish at infinity or something like that, then the dual of V is just L1 of n, which is sequences Bi with sum of Bi being less than infinity. And we can then pair V with this space here just by taking the sum of AI Bi, which will converge and be an element of the real or the complex numbers. However, if we take the dual of this space, we get something bigger. So this is now going to be L infinity of n, which is bounded sequences. So if these are bounded sequences Ci, then sum of Bi Ci is now well defined, provided the Ci's are bounded. And this is obviously bigger than that space there. So even if we define the duals using a topology on these vector spaces, the double dual can still be bigger than the original space. If we take the triple dual, things get even weirder. This is something to do with contents on a measure space n, which are a bit like measure, except they're only finitely additive rather than countably additive. And moreover, in order to find elements of them not in this space here, you tend to have to use weak versions of the axiom of choice, and the answer depends on which model of set theory you're using and so on. So it all gets rather complicated. Anyway, we're not going to worry about the infinite dimensional case because this is an algebra lecture, so we don't go putting topologies on things very much, and we just want to construct an algebraic dual. So what else can we do? Well, we can look at modules over a ring and try and find a nice duality. So if our ring is R, I'm going to take R to be commutative because this works for non-commutative rings, but you then have to remember whether you're working with right modules or left modules, and it confuses me. So let's just make this commutative. First of all, we can define the dual of a module M to be Hom of M to R. And then if M is free and of finite rank or finitely generated, the theory is very much like vector spaces. We find that the rank of M is the rank of M, the dual of M, and the double dual of M is naturally isomorphic to M because there's a natural map from M to its double dual, just as for vector spaces. So, so for free modules, nothing particularly new happens. There's one variation we can do. We can look at projective modules. So you remember, if we've got a finitely generated projective module, then there's another projective module such that the direct sum of P plus Q is isomorphic to R to the n for some n. So this is nice duality. And if a module has some sort of nice duality theory, in other words, if it's isomorphic to its double dual and so on, then all direct summands of this also have this property, because P plus Q dual is obviously just isomorphic to P dual plus Q dual and so on, and the same for double duals. So we find the natural map from P to the double dual of V is again an isomorphism. So finitely generated projective modules over a commutative ring again still behave pretty much like vector spaces. They've got a nice duality theory. What about non-projective modules? Well, let's take our ring to be the integers, and let's take our module m to be z over 2z. Well, then m dual is hom over z from z over 2z to z, which is just 0. And this is a total failure if you're trying to find a nice duality theorem, because you don't want the dual of a non-zero module to be 0. So duality doesn't seem to work for non-projective modules. Well, actually it does, but you have to change things around a bit. What we're going to do is define a different sort of dual. So this time we're going to define the dual of m to be hom of m, hom over z from m, to, well, we're going to use q over z for reasons that will become obvious fairly soon. And this is called a sort of dualizing module. And there's not a single choice of dualizing module. For instance, earlier we used hom over z from m to z as our definition of dual. So in that case we were using z as a dualizing module, and there's no particular reason why you have to use the ring R itself as a dualizing module. We're going to see that sometimes there's a better dualizing module. And again, we have a map from m to m double dual, and what we're going to do is to show this is an isomorphism if m is a finite abelian group. So we've got one sort of duality theory for free abelian groups where we take our dualizing object to be z, but there's another sort of duality that works nicely for finite groups. So let's check this. Well, the proof of this is fairly easy. First of all, we notice that a plus b dual is isomorphic to a dual plus b dual, and m is a direct sum of cyclic groups, because any finite abelian group is a sum of cyclic groups. So it's enough to check that m is isomorphic to m double dual for the special case of a cyclic group, m equals z over nz. And this is easy to calculate because z over nz dual is just all homomorphisms from z over nz to q over z. So, so suppose this is a generator G. The image of G is just an element of order n in q over z, and there are exactly n such elements, which are given by 1 over 0, 1 over n, 2 over n, sorry, of order, should have said dividing n, 2 over n, 3 over n, and so on up to n minus 1 over n. So, so there are exactly n homomorphisms from z over nz to q over z, which just correspond to these elements here. And you can easily see that, in fact, hom of z over nz to q over z is just isomorphic to z over nz. And we seem at first sight to have a natural isomorphism because, you know, we're just mapping the generator G to here as the generator of this. However, this isomorphism is not really natural. Why not? Well, it depends on the choice of generator for z over nz. Well, of course, this doesn't matter for z over nz because there's a canonical generator for this particular group. However, if we had a general cyclic group of order n, there's no canonical choice of generator. And in order to define an isomorphism between a cyclic group of order n and its dual, we actually have to pick a generator. So this is not natural. However, z over nz has the same size as its dual, so we have a map from z over nz. Z over nz is isomorphic to z over nz double dual, and this is natural. Doesn't depend on a choice of generator for a cyclic group. So any finite group is naturally isomorphic to its double dual, and it happens to be isomorphic to its dual, but that's just a sort of accident. There's really no natural isomorphism. And next you can ask, why do we use Q over Z? Well, what is the property of it that we needed? We needed the elements of order dividing n in Q over Z form a cyclic subgroup of order n. So this is the property of Q over Z that we use in order to prove this duality theorem. And there are several other closely related groups we could use instead. For instance, we could use the group S1, which is complex numbers of absolute value 1, or we can also think of it as the reals modulo Z. And Q over Z is actually quite similar to R over Z. There's an obvious injective map from Q over Z to R over Z, so we could use this instead. We could even use the non-zero complex numbers, because the elements of order n in the non-zero complex numbers are just the nth roots of unity, and again these form a cyclic group of order n. So we could use any of these as a dualizing object for finite groups. As an example, let's work out the duals of some finite abelian groups explicitly. So here we have an example. Let's take the dual of, let's do the finite group Z over 8Z star, where this means the unit. Well, yeah, unfortunately, the overusing. Let me put a times sign here. Here you sometimes use star for the units, and unfortunately I'm also using it for the duals. So I'm going to say this means take the units of this ring here. So this consists of the elements 1, 3, 5 and 7. And I'm going to take the dualizing object, or the dualizing module. This time I'm going to take it to be the non-zero complex numbers. So what we want to do is to find all homomorphisms from Z over 8Z times to the complex numbers under multiplication. And there are exactly 4 of these given as follows. So here are the elements of Z over 8Z star, and traditional to use the Greek letter chi for these. So one obvious homomorphism just takes everything to 1. Or we could take these 2 elements to 1 and these 2 to minus 1, or these 2 to 1 and these 2 to minus 1, or these 2 to 1 and these 2 to minus 1. So these are the 4 elements of this group of the dual of Z over 8Z. So I guess this would be Z over 8Z times, and then I'm taking the dual of that. So that's not the double dual. That means I'm taking the units and then taking the dual of that group. So there are the 4 elements explicitly. These are sometimes called Dirichlet characters. So in general, Dirichlet characters are homomorphisms from Z over NZ star to the units of this, not the dual, to the non-zero complex numbers. And they're used quite a lot in number theory. For example, you form a Dirichlet series, which would be L of S, which is given by sum over n greater than or equal to 1 of chi of n over n to the s. And these series were introduced by Dirichlet in his proof of Dirichlet's theorem that there are infinitely many primes in any arithmetic progression, unless there obviously aren't. At this point I'm going to have to stop talking about this topic because it's really number theory rather than algebra. So what algebraic things can you do with these Dirichlet characters? Well, you can do Fourier analysis on finite abelian groups. Okay, Fourier analysis is usually analysis rather than algebra, but if you're doing it on finite groups, it's really algebra. So how do we do this? Well, first of all, you notice that the Dirichlet characters chi I and chi j are orthogonal if I is not equal to j. Well, what does that mean? Well, we can define an inner product on functions by defining fg to be sum over g in the group M of f of m times g of m, and I probably want a complex conjugate somewhere on that. So here f and g are complex functions on the finite abelian group M, and we're just defining an inner product in the obvious way. And what this means is that chi I, chi j is equal to 0 if I is not equal to j, and it's obviously equal to 1 if chi I equals chi j, because then you're just, sorry, it's not equal to 1, it's equal to the order of the group if chi I equals chi j, because you're just summing the number 1 over the order of the group. So we want to show these are orthogonal otherwise, so we want to look at sum over g in M of chi I of g times chi j of g. We want to take the complex conjugate. And this is just the sum of g in M of chi I over chi j of g. Because taking the complex conjugate of a character is just taking its inverse. So we want to show that the sum over g in M of chi of g is equal to 0 if chi is not the unit character. In other words, if chi of h is not equal to 1 for some h. And we can prove this as follows. What we do is we look at sum over g in M of chi of g is equal to sum over g in M of chi of g times h for any h, because this also runs over the elements of g. And this is equal to sum over g in M of chi of g times chi of h, because chi of h is a character, which is equal to chi of h times sum of g in M times chi of g. And now let's look at this expression. Well, this sum is the same as this sum here. So we're saying this sum is equal to this sum times chi of h. So either chi of h equals 1, or the sum in g in M of chi of g is equal to 0. So if chi is not the character that's 1 everywhere, then this case holds for some h, and therefore this sum must equal 0. So the characters of a finite group form an orthogonal basis, so that the set of characters chi I is an orthogonal base for the inner product space of functions on the finite group M. And if we've got an orthogonal base on a vector space, we can write any vector as a sum of as a linear combination of these. So we're going to have any function f is going to be some normalizing constant times sum over I of f of chi I times chi I. So it's just the usual way of writing a vector in a Euclidean space in terms of an orthogonal base. This constant depends on the norm of these. And this is actually really just a Fourier series. So let's see why this is an analogue of Fourier series. Well, instead of taking G to be a finite group, we could take G to be an infinite group. For instance, we could take G to be the integers, and then the dual hom from our group G to C star, sorry, not to C star, let's take it to S1, the complex numbers of absolute value 1, is going to be just S1. And if we take G to be S1, then the homomorphisms from continuous homomorphisms from S1 to the complex numbers will just form a copy of Z. So if we allow our group G to be infinite, we find the dual might not be isomorphic to it, but the double dual quite often is. In fact, it turns out that if this group G is locally compact, then it's isomorphic to its double dual in this sense. So it doesn't just have to be finite, it can be locally compact. We could even take G to be the reals, and then its dual is also given by the reals. The dual is sort of given by mapping y to e to the 2 pi I xy, or something like that. And now we can sort of do this trick of writing down the characters as an orthogonal base, at least if the characters are a discrete set. And this expansion, in the case of functions on the group S1, turns out to be essentially the expansion of f as a Fourier series, and this is the usual formula for the Fourier series coefficients in a slightly disguised form. And similarly, if you take G to be the group of the reals, then this formula, if you replace the sum by an integral, turns out to be Fourier transform. So this case kind of gives you Fourier series, and this case here gives you Fourier transforms. So the theory of duality of modules of rings turns out to be very closely connected with Fourier and with the theory of Fourier series and Fourier transforms in analysis. They're sort of formally the same thing, except you put a topology on your groups and you integrate instead of summing and so on. Now I want to give an application of duality to injective modules. So first of all, what is an injective module? Well, an injective module is a sort of dual concept of a projective module. So let's remember what a projective module is. So a projective module says that if you've got a surjective map of modules and you've got a map from your projective module to P, then it can be lifted, not necessarily uniquely, to a map from P to B. So this is the definition of a projective module. And what we want is to dualize this in the sense of category theory, which means we reverse all the arrows. So I'm going to define an injective module like this. Suppose we've got a map like this. So C is a submodule of B, and suppose we've got a map from C to our injective module I. Then by definition there should be a extension of this map from B to I. So what it says is that I is injective means we can extend maps from a submodule C to I to the whole module to I. So it's very easy to construct homomorphisms from modules to I, because we can always extend homomorphisms from submodules. So let's see some examples of injective modules. Well, obviously the module 0 is injective. Let's work over the ring R being the integers for simplicity. And let's try I being the integers. Is this injective? Well, let's have a look. We've got a extension. We've got a. We can take z to be a submodule of z if we we can find an injective map from z to z if we just multiply by 2. And now suppose we take the identity map from z to z. And we ask, can this be extended to a map from z to z? And the answer is obviously not, because we would have to take the image of 1 here, which is just 1, and it would have to be it would have to be twice something in order for us to extend this map here. So z is not injective. Well, let's try something else. Let's try I equals z modulo 2z. Well, pretty much the same thing goes wrong. If we take the map 0 goes to z over 2z goes to z over 4z, we can take the identity map from z over 2z to z over 2z. And again, if we try to extend this, we can't, because we would again have to divide the non-trivial element of this by 2, and we just can't do this. So it's not actually all that easy to find injective modules. If we look at finite abelian groups, the only one that's injective is the 0 module, and you kind of begin to wonder if there are any injective modules at all. Well, actually there are. If you look at the problem with both of these, was we had this problem that we wanted to divide by 2 in both cases, and we couldn't always do it. Similarly, we see that if m is injective, this implies m is divisible. So what does this mean? It means that if n is in z and n is non-zero and m is in m, we can find r in m with Rn equals m. This isn't really a division of m by n, because R might not be unique. There will in general be many different elements R, but so what this means is we can sort of divide by n in a possibly non-unique way, provided n is non-zero. So by extending the examples we gave, it's easy to see that m is injective implies n is divisible. You just look at 0 goes to z over nz, and you map the element 1 to some element m of m, and then extending this means that m has to be divisible by n in some sense. So injective certainly implies divisible, and in fact something similar is true over any rings. Over the integers, the converse is true. Divisible implies injective. This is false for general rings. It's true for principal ideal domains, but not usually true for more complicated rings. And this makes it easier to find lots of examples of divisible rings. For instance, the rational numbers are divisible, so that they are actually injective. So let's see why divisible implies injective. So what we have is we have a injective map of rings, and we've got a map from C to our divisible group, say it's Q, and we want to extend it to B. So we want to extend F to B. And let's pick some element B in B with B not in C. And then we can suppose NB is not in C for any n. Well, then it's easy to extend. We can just put FB equals 0, or for that matter we could put FB to be anything in Q, and that would give us, you can easily check that gives us an extension. So F of C plus NB is then just going to be f of c, and because NB is never in C, you can check this is well defined. Now suppose NB is in C for some n greater than 0. It should be n1 0. And then we pick the smallest such n. Well, then what you can do is we can extend f to b by putting f of b equals r, where nr equals f of nb. So this is an element of C, so f of nb is defined, and you can check that this gives an extension of b to this extra, so an extension of f to this extra element b. And now we just sort of repeat this. We keep on extending f to more and more of b, and what we should do is we need to use either the axiom of choice, or we need to use some version of Zorn's lemma. You can sort of quote the magic word Zorn's lemma in order to choose a maximal extension of f, and then this argument shows this maximal extension must be the whole of b. We found one injective module over the integers, and we can find other examples. So q over z is also obviously divisible, so it's injective. There's a slightly unexpected thing we can do with q over z. We can actually write q over z as a direct sum of other subgroups. So it's going to be the sum over MP, where MP is the elements of order a power of P for P prime. I always find this a little bit weird, because you think of q over z as being not too different from the circle group r over z, and r over z is certainly not a product and doesn't split in any sensible way, at least not if you take its topology into account. However, q over z, which looks, if you draw a picture of it, it kind of looks like a circle, or at least a dense subset of a circle, does actually split as a product in many ways. And these modules here are also injective. So we've got a reasonably large supply of injective modules. In fact, we have lots of injective modules. More precisely, there are enough injective modules. So what does enough mean? Well, it means that any module m over the integers is a submodule of an injective module. This turns out to be very useful in homological algebra, because you study modules by embedding them into injective modules. So let's see why this is true. Suppose we've got a module m. We want to find an injective module such that m is a submodule of it. Well, let's pick some little element m in m. And then we can map the submodule, then we're going to map m to some element q in, say, q over z, with q not equal to 0. This is provided m is not 0. And we can do this because q over z has elements of any finite order. So whatever the order of m is, we can find an element of q over z of the same order and just map it to there. Then we can extend this map to the whole of m as q over z is injective. So we've used two properties of q over z. It's got elements of any finite order and it's injective. And if we do that, then we can find a map to m which is injective on this particular element. Well, we've made this map injective on one element, but what about all other elements? Well, now we take a copy of Q over Z for each M in M with M non-zero. So we're now going to map M to this product of copies of Q over Z. And for each copy of Q over, and for each element of M, we're going to map it to something non-zero in the associated copy of Q over Z. So this map will then be injective. And this group is also injective. And this is getting a bit confusing because I'm using injective in two different senses. So this is an injective morphism. And this thing here is an injective module. So we've got an injective map from M to an injective module, which is what we wanted. Incidentally, this module is usually huge, at least if M is infinite, because it's going to be a countable or infinite product of usually infinite objects and will then generally be uncountable. We can usually find a rather smaller module, injective module containing M. So let's look at some examples of slightly smaller injective modules. First of all, for the integers, we can just embed them into the rational numbers, which is a lot smaller than doing this. If we've got the integers modulo p, we can embed it into this module mp that we had earlier. You remember mp was the elements of order a power of p in Q over Z. And mp has a subgroup of elements of order p, and this is contained in a cyclic subgroup of elements of order p squared, which is contained in elements of order p cubed, and so on. So this injective module is an increasing union of finite cyclic groups. And in fact, it's the smallest injective module containing Z over PZ. And similarly, Z over P to the NZ is also contained in this module here. Notice, by the way, that these modules are not finitely generated. And in fact, injective modules are in general, they're not finitely generated. I mean, they can sometimes be finitely generated. For example, vector spaces over a field are finitely generated injective modules. In fact, in some ways, injective modules are better than projective modules. There's always a unique, essentially unique minimal injective module containing a given module. So this is called the injective envelope, and this happens to be the injective envelope for Z modulo PZ, and this is the injective envelope for the module Z. I'm not going to prove existence of injective envelopes because you don't really need it very much, and it's actually a bit tricky to prove. By the way, this is better than projective or free module because you notice there's no minimal free module mapping onto a module M in general. At least there's not a unique minimal one. There's a unique minimal injective module that M embeds into, but there's no unique minimal free or projective module. You can see this even if M is Z modulo 5Z. So it's just got 5 elements, 0, 1, 2, 3, 4. And you can say, well, it's obvious how to obtain M as a quotient of a free module in a minimal way. You just take Z and map the element 1 of Z to 1. But the trouble is, this isn't the only way of doing it. That would mean that 1 and 4 are the image of generators of Z modulo 5Z, but you could also map a generator to 2 or 3. So there are two quite different ways of writing M as a quotient of a free module, and there's no sort of canonical way of doing it. Actually, there is a sort of analogue of injective envelopes where instead of using free or projective modules, you use flat modules, but that's sort of rather difficult to prove and doesn't seem to be all that useful, so I won't say anything more about it. Well, that's done injective modules over the integers. What about injective modules over more general rings R? And doing it for the integers was quite messy. So for general rings R, it looks as if it might be even worse. But fortunately, it turns out to be very easy to sort of lift injective modules from the integers to the reals. And the key point is that hom over R, hom over Z from R to I is an injective R module if I is an injective Z module. And we've got lots of injective Z modules I, so this is going to give us lots of injective R modules. And you've got to be rather careful here to make note of what ring you're working over. So here I'm taking the homomorphisms over Z, and this is not I'm thinking of this as being an R module. And we can make this into an R module because R acts on this R bit here. And the reason for this is, well, if we want to show something is injective, we've got to study maps to it. You remember the property of being injective says that if we've got a map to it from a submodule, we can extend it to a map to it from a bigger module. So we want to look at what are the homomorphisms over R from a module M to this module here, to the homomorphisms over Z to R over I. So in order to show this is injective, we need to understand these objects here. And what you've got to be really careful of is we've got an R here and we've got a Z here. So these are not the same. And here we're thinking this is an R module. And the key point is that this is naturally isomorphic to hom over Z from M to I. And again, we've got to be really careful that we're taking homomorphisms over Z, not over R. In fact, it wouldn't make much sense to take them over R because this is not an R module. And now I is Z injective, means we can lift homomorphisms from submodules to full modules. And since we can do that here, we can also do it on this side, and this means that we can lift homomorphisms from submodules to this to homomorphisms from modules to this, because we can do it on this side. So it implies that this thing here is an injective R module. So this gives us a large supply of R modules we can take that are injective. We can take any injective abelian group and just take this group here. And if we take I to be, say, Q over Z, there will be lots of homomorphisms from R to Q over Z, so this will give us lots of R modules. It's easy to deduce from this that there are enough injective R modules. So easy exercise to kind of copy the proof that I gave for the integers and use these modules to show there are enough injective R modules. So you notice that what's really going on here is a sort of duality. If we take I to be Q over Z, then this is really the one of the definitions we gave of the dual of a Z module. This was the dual for Z modules that works nicely for abelian groups. So we're using duality of Z modules in order to construct injective modules over arbitrary rings. Okay, I think that's about enough about duality and injective modules. So next lecture will be something about limits and co-limits and possibly a bit of homological algebra.